Welcome. In this explainer, we're going to take a deep dive into the research paper, Geometric Manifold Rectification for Imbalanced Learning. What's so interesting here is that it proposes a novel, topology-aware framework designed to address one of the most persistent challenges we face in machine learning, class imbalance.
So, we're going to follow the paper's logical arc. We'll start by establishing the core geometric problem, then we'll look at the author's critique of existing methods. After that, we'll introduce their solution, GMR, detail its theoretical underpinnings, and finally, wrap up by reviewing its empirical validation.
All right, so the authors kick things off with a pretty bold claim. They argue that the real difficulty in imbalanced learning isn't just about the class ratio. No, it's a much more fundamental issue of data topology. The problem, as they see it, is the geometric relationship between the classes, specifically how majority samples intrude into the minority space. That's what really degrades performance.
And this visualization here just perfectly illustrates that core concept. You can see the majority class intruding into the minority class manifold. This overlap creates a really ambiguous region, and that's what obscures the true decision boundary and messes with the classifier.
The authors give this a name, topological intrusion. And this perspective is key, because it implies that any effective solution has to perform a kind of topology-aware data rectification. It's about more than just tweaking the class ratios.
So, with this geometric perspective in mind, the paper naturally moves into a critique of traditional data cleaning techniques, like, for instance, Edited Nearest Neighbours, or ENN.
And the critique really boils down to this fundamental mismatch. You see, traditional methods apply symmetric cleaning rules. They treat every sample the same. But the problem itself is inherently asymmetric. The cost of mistakenly removing a rare but really informative minority sample is just so much higher than the cost of keeping a noisy majority sample.
This leads to two pretty critical flaws. First, you have this flawed symmetric treatment that just completely ignores the different information value of the samples. And second, there's a total neglect of the local manifold structure, because uniform voting schemes, well, they produce coarse and frankly unreliable confidence estimates.
So to address these specific limitations, the paper introduces a new framework they call Geometric Manifold Rectification, or GMR for short.
The whole objective of GMR is to rectify the data manifold. It aims to transform it from that messy state of topological intrusion to one of real clarity. And it does this by selectively removing those intrusive majority samples while, and this is crucial, preserving the integrity of the minority manifold.
Now, the core mechanism of GMR is all about its confidence estimation. As you can see here, it calculates a geometric confidence score using inverse distance-weighted KNN voting. What this does is it gives much more influence to closer neighbors, which means it actually respects the local geometry of the data manifold.
Okay, let's break down the two main contributions of the GMR framework, its confidence estimation and its cleaning strategy.
The framework really operates as a two-stage process. It starts with this robust geometry-aware confidence estimation, and that estimation then informs a cost-sensitive, asymmetric cleaning strategy. It's a really elegant flow.
And this design isn't just some clever heuristic, it's actually theoretically motivated. Theorem 3.3 in the paper lays it out. It establishes the conditions where this geometric weighting scheme really pays off. Specifically, in regimes where estimator variance is a bigger problem than bias, this approach is proven to reduce the mean squared error of the confidence estimate compared to standard uniform voting.
And if you look at the implementation details, they directly encode this whole philosophy. You've got an adaptive distance metric, you have explicit asymmetric thresholds. It all reflects the different misclassification costs and the information value of each class. It's all very deliberate.
All right, so after laying out the theory, the paper moves on to an extensive empirical validation to really demonstrate that GMR works in practice across a wide range of conditions.
And the results are pretty impressive. Across 27 benchmark datasets, 7 different classifiers, and 18 baseline methods, GMR achieves the best overall average rank of 4.22. That signifies consistently strong performance across the board.
This heat map here does a great job of illustrating GMR's classifier-agnostic nature. The results clearly show a consistent performance uplift when GMR is used as a pre-processing step. And it doesn't matter if it's for linear models, tree-based ensembles, or instance-based learners. It helps them all. And it doesn't stop there. GMR also shows its utility as a lightweight preprocessor for modern deep tabular models. For instance, it enhanced the performance of the tab DDPM diffusion model on several pretty large-scale datasets.
There was even a supplementary experiment that suggests the GMR principle could be generalized beyond just tabular data. By applying GMR to feature embeddings from a ResNet model, it actually showed promise for long-tailed image classification tasks, which is a really interesting direction.
So the research concludes by identifying some key avenues for future work. It leaves us with these big, forward-looking questions. How can we extend these geometric principles to multi-class imbalanced settings? And can we develop methods to let the hyperparameters select themselves adaptively based on a dataset's specific characteristics like overlap and noise? Definitely a lot to think about for what comes next.